Thank you for watching Idealized Science Institute's long-form videos. Here, our goal is to help teachers teach purposefully. We have deliberately slowed down the process so teachers can dissect the lessons and find those hooks that will engage their students in authentic scientific practices. Now, these lessons are sequential, so please watch them in order. And if you like what we're doing, consider supporting the Idealized Science Institute. Visit our website where you could see other long-form videos, our podcast, we have quick quizzes, and so on. And as always, please put comments down below. And we are really hoping to hear from you as you enact some of these lessons in your classrooms. As your students are working through this problem, be mindful of what we are out for. Science and engineering practices, again, include asking questions and defining problems. And we're doing that. Developing and using models, of course. Planning and carrying out investigations. This is what you want them to do. You want them to have hand in how the experiment is being designed and implemented. Analyzing and interpreting data. They're getting data. They're getting feedback from nature. They just found out they're getting a 20% error, probably unhappy, which they should be. So they're interpreting that data right now. And then you think, are they using mathematics and computational thinking? Of course, and they're about to use a lot more. Constructing explanations for science and designing solutions for engineering. Hopefully, we're going to figure out a way to explain where that error came from, maybe even get rid of it. And engaging in argument from evidence. You can't say we've done a good job when the numbers are 20% in obtaining, evaluating, and communicating information. The more that they're speaking with one another and to each other, the better. Remember, the guide values argumentation in the classroom. And it talks, using this chart, three spheres of activity for scientists and engineering. But it all comes down to argumentation and critique. So keep in mind, we're doing exactly what we should be doing. And I'll come back to this. But let's go over and see what kind of ideas we have. When you come to check on the students, you can see that their ring stand is now fixed to this bar system, stabilizing it to a great degree. Now when you were to drop the ball, it doesn't move the apparatus in any way. So that's an excellent thought. However, this 20% factor just seems so high that it just can't be that alone. And the problem is something that we already talked about. When we drew this picture out, we showed the ball almost the same size as the tube. That there is part of the problem. When we dropped the ball down, we could hear it either banging on the side or scraping on the side. In fact, it might actually roll when it ends up scraping, taking off some of your energy, scrubbing that off. So that's one of the problems. So you might think, well, maybe we should go back to the small ball. The small ball would never hit the sides. But again, even if we repeat this, we'd probably end up with even a higher error with a small ball. How can that be? Well, it's the geometry of the ball itself. That's the problem. And while our picture shows that we have a certain distance from photogate to photogate, and when a ball is going through here, we can see that its diameter should block the photogate, but it doesn't. And here's why. Let's say that we have this small ball falling down here, and you can see the photogates. They might not be perfectly lined at this point, but let's pretend that the beam is coming straight out towards us. If the beam only catches the edge of the ball, then we are not going to end up having the appropriate diameter. Because when we put these into our caliper and we get our measurement, we are saying the diameter is going to go through the beam. But it doesn't always. In fact, it would be rare for it to. Let me draw this out. Draw a circle. And let's say we'll use the same apparatus that we have here, except now what I'll do is I'll simply turn the photogates so they're facing us. now just think of that dot as being the beam going through, like going straight in, kind of like if I put a dot there and if I put a dot right here. If we used a very small ball, we might find that the ball altogether misses the beam. So if that ball is falling down, it might miss the beam entirely. But even if I had a slightly larger ball like this, you can see that it's only going to cut that small distance right there. That's going to be a small distance as compared to the whole diameter of the ball. And that's the problem. When we put the diameter, we're assuming that the beam cuts through the diameter. And it probably doesn't. In fact, most of the time, it probably won't. If you ended up having a ball that was almost perfectly fit in there, you increase the friction. And now you know for sure that the beam is going to go through the diameter, but you also know for sure it's going to rub up against the sides. And you're going to have to push all of that air out of the tube. That's a problem. So the bigger I go, the more friction becomes a problem, and the smaller that I go, the less chance I have of actually hitting the beam. In both cases, it's rare that you would ever get the diameter. That explains why we're going to have such a large error. You let students know about this particular problem, then you ask them if they can come up with another idea. Again, you need to give them a little bit of time to think through this. Hopefully the students have been discussing for a while, and we realize that round objects can be a problem, but not always. In other words, if I were to drop a cylinder down this tube, it is round along this axis, but when you look at it straight on, it looks like a rectangle. And so if you were to use some kind of cylinder like this, it's actually always going to have the same exact distance. And so using a cylinder is a much better idea. But then we need to ask, well, if I were to use a cylinder, should I use a thin or a thick? I think most of us can figure out right away that if I use a thin, it might go right past the photogate beam without ever hitting. Or it might just fall at a slight angle and only catch a small portion of it. But if I end up having a cylinder that almost fits perfectly, then I'm going to have that friction problem again. I mean, really, we should never hear the object falling down the tube. It should fall straight down through. This tube is simply like a guide rail to protect our photogate. So in this case, if you use too small of a diameter in terms of your dowel, you're going to have a problem. But if I use too big of one, I'm going to end up having an air friction problem. So what if I were to use a very large dowel? This is going to be nearly an exact fit in here. This is going to be great, but again, we have that air friction problem. So maybe I should use a smaller but shorter dowel. And a shorter, smaller dowel like that seems like a good idea. Let's just think of that, though. In other words, should the dial, which is going to act just like a rectangle according to the beams, should I use a short or a long, or doesn't it matter? The students will start to recognize, if I made this a perfect square, if it didn't fall and it was short enough, I could literally get that square to end up falling in this direction. And if this is a length L, if I were to turn it on its side and go from the sharp point to the sharp point, it is going to be a much bigger distance, a longer length. In other words, this distance is going to be smaller than this distance. So we don't want this to rotate inside the tube. So the answer is, the longer the piece, the less likely it's going to be to rotate. And you can draw that in our picture. In other words, if I had a small squarish piece, well, I can end up having a much bigger length than if it were to simply fall straight down, where that is going to end up being a smaller length. So the key is, the longer the dowel, the better. And of course, we want to make sure it doesn't end up rotating. So a longer dowel will only be able to rotate a very small angle. And in fact, if I had a very long dowel, it wouldn't be able to turn at all. So that distance would be true for its length. We could draw that here. So in this case, if I had a dowel that was very long, like this, it can barely rotate in here, just the slightest bit. So you would minimize that difference. The problem here is this dowel is very light, and it's going to be affected by air friction, maybe more than something else. In other words, if I had my choice between this piece of balsa wood or this steel bearing, this one is going to end up, if they're the same size, this one is going to end up having a greater effect from the friction that it's feeling than this mass. So again, it'd be time to let your students think, is there something else that we could do? The students often will say, this should work well, from the conversations we've just had. Others will say, let's get a piece of this metal pole and cut it into slugs that we can drop down here. And that really does work. We're going to minimize the problem that we had with the beam going through a round object. Because again, this looks like, from far away, it looks like a rectangle. And as long as it's long enough and can't rotate, we don't get that extra distance. Dropping something like this down will take our 20% error down very quickly. Students can rerun this, and more than likely they're going to be 5% or less. And that's really, really good. But that's still an awful lot of error. So how can we eliminate it even more? And again, our main concern here is that we have a very light piece of wood, and you're physically doing work. Remember, this is not just able to cut through the air when it drops down. There's air in that tube. It has to go somewhere. So we're going to end up pushing all of that air out. We have to literally get rid of it. But they say, let's use this anyhow. But there was a problem when they did their drop. They could only get one. They would drop this down, and hopefully it would make it through the bottom, but then they couldn't get this out. The tube itself has to be down here. And the problem is this ring stand, along with these poles, is not long enough. So in other words, I can't get the photo gate high enough on this pole. So I can move the pole up so this would come out of the bottom, but then I have to move the photo gates along with it. And the pole's just not long enough. So students will have to figure out how to contemplate with that. First idea they're going to say is, someone's always going to say, let's cut the piece of metal. Wood is, or piece of wood. Wood's easy to cut. We can end up with something shorter, and it'll be able to be pulled out each run, and we can go over and over until, we hear a nice drop. But as we found out, the shorter this dowel, the shorter this rectangle, the more percentage of error we're going to have with the rotation. Eventually, students will finally say, well, we either have to cut the pipe, which we're not going to do, or we can hang that off the side. And that's normally what they do. Let's see what they do. We now have the ability to drop the wooden dowel through the apparatus because the students have taken the pipe and allowed this PVC to hang over the edge of the table. They just took the ring stand, put it on the other side, everything's stable. This is a really nice structure. We can end up hitting collect again. I can just use my mouse. We can end up hitting collect. And then when we drop this down, it doesn't even matter where we drop it from, and I can catch this. By doing this experiment, we are now down to probably, 4% error when you run the numbers. But that's still not good enough. Again, we haven't eliminated the friction problem. The Dow has taken care of the rotation problem, and part of the issue is the measurement. Students will kind of eyeball this, and they'll look and they'll say, okay, I got the length of the Dow, and I'll enter that into the computer. But part of the issue is that on these rulers, often there's a little extra piece that the students forget to take into account. So instead of putting it at the edge of the ruler, you really have to start at that 0 mark. But again, if you have a caliper, calipers are not just good for small round things. This is an excellent way to find out what the length of the Dow is using the caliper. If you put that in, you're probably down to about 3% error now. That's really, really good. But there's still the error problem. So challenge your students. How can we end up getting rid of that last bit of the air friction problem? And we know that we don't want to make the Dow too much wider. It makes the air friction problem worse. And if we use a thinner dowel rod, I don't know where I put it, it can rotate a little bit, and we might miss the beam altogether. At some point, students might think, and maybe you'll have to lead them here, if I use a hollow piece, in other words, a hole, so this is going to be a ring, but that ring to the side looks like it's a rectangle. And notice the length, it's very long, and it's also very dense. So instead of having a very light piece of wood here, I'm going to have a very dense, hollow tube. And now when this falls down the tube, there's almost no air. It can't really have any angle inside here. The length is great enough, so even if we have a little bit of measurement error there, it's going to be a wash. And essentially the air that is in the tube stays there. It's thin-walled. The air stays there, and the pipe literally cuts through the air inside this other pipe. And by ending up with a solution like this, our 20% error, if we get a drop and we put a level on both sides, we can end up getting less than 1% error. In fact, if I drop this straight down, I shouldn't hear anything at all. It should just be as silent as that falling. If you hear scraping, then you know that you've taken a little bit of your velocity off. So it's this type of iterative process of fixing all of these problems. That's what you want to engage your students with. One of the problems that teachers often have is they try to student-proof all of their verification labs. They write everything out. And that's not going to help the students develop those thinking skills that'll help them be either a theoretical physicist, an engineer, or a good mechanic, or a construction worker. All of these things will transfer. It is learning how to assess your instrumentation and figuring out how to assess how is my experimental design, how are my measurements coming about, where is the error. And by doing that and allowing students to engage in the multitude of little problems that arise naturally, you're denying them the lessons that could be learned. And as a teacher, if you're thinking, well, maybe I'll make sure that the length of the pole is going to force the students to think that they have to hang this off the edge. You don't have to do any of that. There will be enough things that will naturally happen in any type of experimental work that you don't have to purposely put anything that's going to confound the students. Just be as honest as you can in the experiments. They'll pop up. And again, you've got to dedicate time with your students in class to thinking through these. And I know this is a very difficult thing. Many teachers have this push on them to get through a certain amount of content, which is usually too much. So You probably can't do a lab like this every day, but you can at least do one of these a year. And then if you figure out how to be more efficient other times, you might be able to get a second one in, or a third. And remember, this is really what the standards, the new standards framework is all about. So if you're really getting a push for the next generation science standards, or any other standards that are based on those coming out, make sure that you look at those. Show them to whoever's evaluating your lessons that this is what we're being asked to do. This is what we're supposed to do. We're supposed to argue using evidence and allow students to develop science and engineering practices. So we hope this is helpful, and good luck on your experimentalism in your class.